Good evening. Today I'll be conducting the week 6 problem solving and doubt clearing session for the course control and tuning methods and switch mode power converters. So today we'll be looking into the following. We'll be discussing about the small signal modeling, what transfer functions we develop from that. Then we'll discuss about the closed current loop small signal modeling, the transfer functions we get through that. Next, we will discuss about the impedance analysis, like for the input impedance, like what is the significance, etc. Okay, and then we'll solve some questions. Okay, so this is your week 6, where we are doing small signal modeling. So can you tell me what are the various transfer functions we develop, which are developed?
GVD, that is a control to output transfer function.
Okay, so one is GVD, that is control to output transfer function.
Then GVG, input to audio susceptibility, input to output.
So this actually is V output of S by D tilde of S. GVG is input to output transfer function. Your GVG of S is V output tilde of S by V input tilde of S. Okay. Then what is the next one?
Input impedance and output impedance.
Yes, so next is your input impedance. Where your Zn of S is equal to V in tilde of S by I in tilde of S. Fourth is your output impedance, that is Z out. That is your output impedance. That is your Z out of S is minus the output of S by out tilde of S. Okay. So what do these mean? So these are for a DC to DC converter. Okay. Where we have this DC-DC converter. Okay. Where we have this is our input voltage. This is our input current. Over here, you have your V output. You have your load R. Then you have this external current load I output tilde. Okay. Let us say I output for the time being. So now, this DC-DC converter is driven by a duty D. Okay, by a duty D. So what we first saw last week is we have to do modeling. Modeling is like we are finding out a mathematical model of our converter. And when we do that mathematical model, what we do is we average over a time period T. We average over the switching time period. Okay. Now, why do we find out all these transfer functions? That is your GVD controlled output transfer function, GVG, Zn and Zout. So your GVD is what? V output tilde of S by D tilde of S. That means whatever is the change in your control input, how does it affect your actual output? That is the significance of this transfer function. So this transfer function you will use a lot when you're doing voltage mode control. Because you want to see what is the effect. If you change your input, your control input, how your output changes. Next is your input can fluctuate, right? Your input voltage, which you're getting from the grid, that may fluctuate. You might have noticed sometimes your fan will work faster, slower, lights are dim or more bright. Etc. Those dependent on input fluctuations. That's why many times we, for very sensitive equipment, that is like your speakers or your public address systems, we use what is known as a stabilizer, such that we give the stabilized voltage to our sensitive equipment. So now, so whenever there is a fluctuation, that is, whenever your input will fluctuate, your output also could fluctuate. It will fluctuate, right? Because it is dependent on your input. So that determination, the effect is given by GVG of S. That will give you V output tilde of S, that effect divided by changes in your input voltage. Similarly, how does this look like? For your external thing, this is your input impedance. That is, this DC-DC converter is acting as a load for, like a practical voltage source, or there's another DC-DC converter before this. Then that is known as your input impedance. Okay. Similarly, this portion from this side, how it looks, that is known as your output impedance. Okay. So any queries till this point?
No, sir.
Okay. So these are various impedances and transfer functions which are there for your DC-DC converters. Similarly, sir had taught about yeah. So when you're determining, let us say this GVG of S, let us consider you are focusing on GVG of S. GVG of S is what? Changes in output when there's a change in input. When you do this, you have to assume your converter is operating in steady state for all other variables. That is, your D tilde is 0 and I output tilde is 0. That is, your I output is fixed, your D is fixed. So that changes is made to 0. So you're individually seeing the effect of your input voltage. Okay, you're individually trying to assess what is the effect of the change in input voltage fluctuations in your output voltage. What is the effect? Okay. Then, so this is one aspect. Another thing is you have your GVG, that is giving your input voltage fluctuation, that is generating some fluctuation in your output voltage. Similarly, you have your GVD, right? These are giving fluctuation in your control input. These all get added. Similarly, you have your output impedance, and this is your I output perturbation. So all these together effectively form your B output perturbation. That is, we are seeing the contribution of each of these transfer functions. So your perturbation in your V output is dependent on your perturbation in your load current, perturbation on your input voltage, perturbation on your duty. Okay. Then, let us say you are finding the transfer function you have got. You have found a transfer function. Your transfer function is GVD of S. Okay. That in the case of a buck converter, it is being to let us say it is 1 plus SL upon R plus S square LC. This is for a buck converter. Okay. So this is what your GD of S is V output tilde of S upon V input tilde of S. Sorry. It is D tilde of S. Okay. This is V in 1 plus SL upon R plus S square LC. Okay. Now, what you must understand is, what is the DC gain of this? Can anyone let me know? We have many people here. What is the DC gain? Like, what is the significance of this, right? You have one is known as the DC gain. Okay, someone let's type. Okay, DC gain is mean. Okay. Now, how many zeros are there?
No
Yes,
zeros.
no zeros. Okay, there are other people also. There's HP, Parvati, Vidya. There's also an answer, right? So zeros are
Yes, sir.
okay. How many poles are there?
2.
2 poles are there. Okay. So that means this is a second order transfer function, right? Now, do you remember the various types of second order transfer functions which are can be there? Like what can be a different types of transfer functions for a second order system?
Underdamped, damping ratio,
Yes, exactly. So you can have underdamped,
critically damped,
critically damped, or you can
overdamped.
overdamped. Okay. Now, where are the poles located for an underdamped case? When the system
Delta less than 1.
your zeta is less than 1. This is true, but where are the poles located? How do we find out the pole locations? So in the case of underdamped, they are complex conjugates, right? That is, your poles is something minus zeta omega n plus or minus j omega n squared of 1 minus zeta squared. So these are complex conjugates, right? In the case of critically damped, there are two real poles at the same location. And in the case of overdamped, two real poles but at separate location. Okay. So if you will give a step input in the underdamped case, it will oscillate like this. In the critically damped case, it will reach like this. In the overdamped case, it will take time. Okay. So that is how your damping affects your response. That is one case. Okay. Now, I think it's better if we do this with an example. Or let us start with the questions. That way we can proceed faster with the example. Just go. Which of the following transfer functions can be an improper transfer function? Like as Arun has told, there are these 4 different types of transfer functions. You have control to output transfer function, you have input impedance, you have output impedance, you have audio susceptibility, right? You have 4 transfer functions. So which of the transfer functions can be an improper transfer function? So what is an improper transfer function? Say we have started question.
Numerator, degree of numerator no greater than degree
Okay.
of denominator.
So the degree of numerator, if it is greater than the degree of the denominator, then it is known as an improper transfer function. Okay. And that is happens only for your input impedance. So I thought of doing for the boost converter one example. So there we will check, okay, what is the input impedance, how it is improper. Because in the input impedance, what you will get numerator is second order, denominator is like first order or something. Okay. So that's the concept of input impedance. Now, for the second question,
Sir, what about output impedance?
output impedance is usually it is the same order as your converter. That is, the denominator has the same order of your converter. So it will be proper transformation only.
Okay.
Input impedance is like a special case, and maybe it's better to use input admittance rather than input impedance. Okay. Acha, I'd like to ask one more question. So for your DC to DC converter, should the output impedance, let us say the input impedance should be high or output impedance should be high? Okay, let me reframe my question. You have your DC-DC converter. Let us consider only output impedance. For DC-DC converter, output impedance, should it be high or low? What do you think?
It should be low.
Okay, why low?
Because irrespective of load current, it should give proper output voltage. If the output impedance is high, for higher load current,
Yeah, so
there will be more drop.
your DC-DC converter is acting like a voltage source, right? So that means you want the characteristics of a voltage source. So for a voltage source, you want your output impedance to be as low as possible, right? Okay. So that is regarding the output impedance. Okay. Go to the next question. Input impedance. So what is true about the input impedance? Huh?
B and C seems to be correct.
Okay.
Then in the first question, input impedance, if it becomes improper transfer function, then we cannot realize.
Yes. Okay. So this is question number 2. So this is regarding input impedance. So this is your Zn of S, right? What happens is Zn of S, your degree of your numerator is greater than the degree of your denominator. Let us just give one example, some numbers. Your Zn of S would be some S square plus 8S plus 12 upon S plus 5. Okay? In here, the degree of the numerator is 2. Here, the degree of your denominator is 1. Now, such a transfer function is not physically realizable because any transfer function to be realizable, the degree of your numerator is less than or equal to your number of your denominator. Okay? It's not physically realizable. It's not a proper transfer function. No. It is there. It is effectively computed like that. But if you would make a system, actual system with such a transfer function, it will not occur. That is why usually if they want to actually properly define it, they should actually use the term input admittance, not input impedance. Because if you flip it, admittance is what? Yin of S is 1 upon Zn of S, right? That is S plus 5 upon S square plus 8S plus 12. Such a transfer function is physically realizable. Okay. Yes. This is one aspect. Then they're saying input impedance is used for MPPT. So MPPT is a very common thing. Can someone tell me? We have Divya, HP, Parvati, Arun. What is the full form of MPPT?
Maximum power point tracking.
Okay, where is it used?
Solar panel.
Okay, good. So MPPT means what? You have your solar panel, right? And you will have, usually we use a boost converter. Okay. So this is your VPV. This is your IPV, right? And this whole block, when it is seen by your solar panel, this is effectively seen as your input impedance, right? It is seen as your input impedance. Now, to extract maximum power, you have to match this input impedance with the impedance of the effective impedance of the solar panel like that, because you want it to operate at this point. So this is your VPV, PPV. This is the point where you get P max, where you can extract maximum power. So you want your voltage to be set at this value. So for that, you have to match the input impedance of the boost converter with the input impedance of the solar panel. And since the solar panel is very slow, okay, solar panel is a very slow thing. Like your sun, it doesn't become dark instantaneously. It takes a lot of time, right? And for the solar panel, if you guys have worked on, you know that the voltage it generates, that these characteristic curves, they change depending on the temperature, they change depending on your irradiation, that is your intensity of your sunlight, etc. Huh? So your temperature, doesn't change so drastically. It's a very slow process. And your irradiation, that is your sunlight, which is coming, doesn't change instantaneously. It is a gradual change. It is not constant. It is gradual change, but it does not change instantaneously. But your boost converter will be operating at a switching frequency, let us say 100 kilohertz, right? So this time period is how much? 100 kilohertz is 10 microsecond, right? So your boost converter is operating very fast. So boost converter is very fast as compared to your solar panel, right? So for MPPT application, it is sort of sufficient to just match the DC gain. You can just match the DC gain, it is fine. All those S terms, all that, their impact comes at very high frequency, and anyway your solar panel is operating slow, so it will not affect the boost converter so much because your solar panel changes very slowly. Okay. And this is for MPPT. Next part is you should have an EMI filter. So can anyone tell me what is the full form of EMI?
Electromagnetic interference.
Yes. That means you have your DC-DC converter here. Before that, you have to connect what is an EMI filter. And this is your supply. And this is your load. This is a very small example, right? So what happens is this DC converter is a switching converter. So the DC-DC converter, is it a linear converter or non-linear? Let us ask Divya, HP, Parvati. Is your DC-DC converter linear or non-linear? They all become very silent. Okay, Arun, what is
Only non-linear.
I couldn't hear, sir.
Oh, okay. Yeah, Parvati is saying it is non-linear. So I asked, is your DC-DC converter linear or non-linear?
Non-linear.
Non-linear. Okay. Next. So we have said DC-DC converter is non-linear. So can you tell me, when it is non-linear, what it will do? It will generate harmonics. It will generate harmonics, right? So to attenuate those harmonics, and also there will be this switching noise, etc. We need this EMI filter. Okay, this is required. Now, when the EMI filter comes into picture, your DC-DC converter acts as a load to your EMI filter. So then we will look from this side. We're looking from this side, and the DC-DC converter, when you from this side, we will see your input impedance of the DC-DC converter. So your input impedance is necessary while you are designing your input EMI filter. Okay, and what happens is also your GVD changes when there is an EMI filter. And sir has told there's this Middlebrook theorem is there, which shows how do we find what is the new GVD, or that is the extra element theorem. Okay, this is for your EMI filter. Next is for impedance analysis, we set the input voltage perturbation to 0. For input impedance analysis, we don't set the input voltage perturbation to 0 because your Zn of S is actually equal to V in perturb of S by I in perturb of S. This is your actual input impedance, where your duty perturbation is 0, your load current perturbation is 0. So in this for Zn of S, you don't have to set your input voltage perturbation to 0. We should not. Otherwise, you will not get the Zn of S. But for the Z out of S, that is equal to minus V output of S by I output of S when your duty perturbation is 0 and your B in perturbation is 0. So in the case of Z output of S, you have to set your input voltage perturbation to 0. But in the case of Z in of S, you don't need to set your input voltage perturbation to 0. Okay? Fine. So we'll proceed to the next question. Okay, this is a very good question. So can you tell me what is the modeling sequence which we have to follow when we are determining a small signal transfer function? No, this is not part of the question. So actually, I prepared the questions in the PC and I'm doing it in a laptop. So the OneDrive was not synced, so the questions did not get properly modified. So I have to again retype the questions. Okay, so
Sir, derive the dynamical equations.
okay, then
Then we can average the dynamics over a switching period.
yes.
And then we can add perturbation.
Yeah.
But there are two options.
That's what these questions were. To retype. No. Okay. You add the perturbation to the average model, then what you do?
From the perturbed model, we can derive the transfer function.
Okay. So actually, you will get a small signal. You get the equivalent small signal model law on circuit. And from there, you determine the required transfer function. Okay. So Parvati, HP, do you have any doubts with what Arun has said? Do you have any queries?
Sir.
Yes or no?
No, sir.
Okay. Anyway, I'll just give some details regarding it. So, when you are deriving the small signal model, you have to follow some steps. So, what are those steps? Right? First is you find out what are the differential equations for your converter. That is usually your L dIL by dt, your C dVc by dt. This is your equations, whatever is those equations. You can have one equation for your input current also. Okay, that is some function of Q into IL. This is for buck. Okay, Q into IL or something. Q into IL like that. Once you get those equations, then what do you do is you average the equations over a time period T, over the switching period. So when you average the equation, what it comes, let us say, let me give an example. You have your L dIL by dt, that is your Vn minus 1 minus Q into V naught. This is for your boost converter. When you average it out, you're averaging it. Basically, what you're doing is you're replacing your Q with D. Okay, you're replacing Q with D. Because Q can either be 0 or 1. Okay, it is either 0 or 1, depending on the mode. But when you average it over a time period, your average of Q actually is D. Okay, so you're getting the average value. Similarly, you're getting the average value of V output also, V input also. Then what do you do is, you add the perturbation. You add the perturbation, that is you put your V output is actually your capital V output plus V output perturb. So this is your DC component, which we had studied DC circuit averaging last time. And this is your AC component. Similarly, your duty D is capital D plus D per term. And this is again your DC part. This is again your small signal AC part. Okay. Similarly, you apply it for all that. Then what you had done is you neglect the higher order perturbations, right? That is, we will consider V output tilde into D is fine, plus V output into D perturb is fine. But this V output perturb into D perturb, this is not acceptable. This we ignore. We are ignoring it because we are considering that the perturbation in duty and the perturbation in the output voltage is quite small. So their products will be even much more smaller as compared to these values. Okay, so we ignore that. Next is from the AC small signal model. If we want to find our transfer function, that is, if we want to find GVD of S, we have to find V output tilde of S by D tilde of S. But what we have to make sure is the other things, that is your V in perturbation we set to 0, your I output perturbation we set to 0. Okay, those things we must be careful to follow. Okay. So this is the step which has to be used. Now we proceed for the next question. This question, where we want to do the modeling of a boost converter, where we are considering this is our input voltage, output voltage, load resistance, L, C, switching frequency, etc. What I want you to do is to determine the small signal model of the boost converter in parametric form. And then we will develop the transfer functions. Then we will consider a closed current loop. And for that also, what is the transfer function? We will look into that. Okay. So now, let us see. This is our question 4. So this is how a boost converter looks, right? You have your Vn over here. You have your L over here. They have told to include your parasitics. That is your inductor DCR we have included. You have your switch R1. This is Q. Your ideal switch and its resistance R1. This is your Q bar. This is your C. And this is your R. Any queries in this? That is, your Q is your main gate signal. Your Q bar is the complementary one. And each switch, I have added a on resistance of the switches. And for the inductor DCR, I have added this RL. That is your DCR of your inductor. So then we will proceed with the same steps which we just saw in the previous question. What we have to first do is, this is my inductor current direction. This is my capacitor voltage or output voltage. Same thing. I do V0. This is my V0. So first, and this is my IC. This is my I0. Okay. Now what do I do is, I will first write the dynamical equations. So when Q equal to 1, what is my L DIL by dt? Can you tell me?
V in minus IL into RL plus R1.
V minus IL into RL minus IL into R1. What is my C dVc dt?
Minus I0. So minus V0 by R.
So we see dV naught of so minus V naught of by R. Okay, when Q equal to 0, what is my equation?
V in minus IL into RL.
This is equal to Vn minus IL into RL. Then
Minus IL into R on minus V naught.
minus V naught. Okay, good. Then what is your C dV C dt? There is a capacitor current.
IL
That is
IL
so
minus
minus.
V0 by R.
So it is IL minus V0 by R. Because that time the path is closed like this, so current will flow like this. So that is this current is your IL, and your IC is equal to IL minus I naught, and your I naught is equal to V naught upon R. Okay. Any doubts in this? So now we have to do the averaging, circuit averaging. So how do you do the circuit averaging? You will. So this is for a period of time dt, and this is for a period of time t. So this time duration of this is 1 minus d into t, and this time duration is equal to d into t. Let us look into it. That is your, this is your inductor current, let us assume. This is your IL. Your Q is like this. Okay. So this time is your dt. Actually, it should be small dt. And this time is your 1 minus d into t. Okay. This is your gate signal Q. And this is how your IL looks. So we want to find the average behavior. Okay. So when you try to find their average behavior, what you will do is, like you have seen earlier, we will get a L d IL by dt. This average part is equal to this part, V minus IL into RL minus IL into R1. So we first divide by 1 by t, and then it is Vn minus IL into RL minus IL into R1 into dt plus, when the switch is off, that is V minus IL into RL minus IL into R1 minus V naught. That is Vn minus IL into RL minus IL into R1 minus V naught into 1 minus dt. Okay. Now how we can simplify this further? What do you think I should do?
V in minus IL into RL minus IL into R on is there in both terms. So
That means my LDIL averaged LDIL by dt. First is I can cancel out t, right? T I can cancel out because it is common. So I cancel it out. Okay. Then this part is common. As Aruna said, this part is common in both, right? So what is d plus 1 minus d? Hmm?
1.
Okay, it is 1. That means I get your V in minus IL into RL plus R1, and then minus of 1 minus D into V0. Okay. And I'm sorry, this should be small d. dt 1 minus D. Okay. Now, what do we do with this now? So this is 1 average equation for my inductor current dynamics. Now we have to do for my capacitor, right? So for capacitor, what do? I have my C dV output by dt. In this case, that is equal to what? My 1 by T into what is my capacitor current for the dt time. For dt time, my capacitor current is minus V output by R. That is dt into minus V output by R. Then plus 1 minus V into T into the capacitor current when my switch is off. That is equal to IL minus V output by R. So that would be equal to IL minus V output by R. So now again, by T get cancelled. Then what is this common? Is anything common or all are unique and different?
Minus V0 by R is common.
Okay. So we get C dV0 by dt is equal to minus V0 by R plus 1 minus D into IL. Right? Okay. Okay, so Parvati, what is the input current for your boost converter? How much is it? He is not answering. What about Divya and HP? What is the input current for the boost converter? I think they all are feeling very shy. So Arun, what is the input current for the boost converter?
IN equal to IL.
Yeah. So in the case of the boost converter, this is your IN. So your IN is equal to IL. Okay, so this becomes easy in the boost converter. In the buck converter as well as in the buck boost converter, it's difficult. So your I in is equal to IL for a boost converter. So now we have done the step 1. We have done step 1 and 2. We have found the dynamical equations for each mode, and then we have averaged the dynamics. Now what will be the next part?
We
Adding
can
Okay. So we add a perturbation. So we add perturbation. Right? So I should add perturbations to what and all? Which and all quantities should I add perturbation?
Voltage.
Okay, output voltage. Then,
Load current.
yeah, inductor current. Yes.
Duty cycle.
Yeah. So you add perturbations. You represent your output voltage as the steady state output voltage and the perturbed output voltage. Your input voltage also you represent as input voltage. plus input voltage perturbation. Your inductor current also you represent as the average inductor current plus your perturb quantity and your duty you represent as your steady state duty plus your perturb duty. Okay. So that we must substitute in which equations? In this equation and in this equation. Okay. So how do we write? We will write L average of D IL plus IL perturb by dt. It is Vn plus Vn perturb minus of RL plus R1 into IL plus IL perturb minus 1 minus D minus D tilde V output plus V output perturb. Right? This for the inductor current dynamics. Next, what do we do? Similarly, for the capacitor current, we also can write C D V0 plus V0 perturb by dt is equal to this is minus of V0 plus V0 perturb by R minus 1 minus D perturb plus 1 minus D perturb into IL plus IL perturb. Okay, this is for the boost converter. Now, what do we do with this? Right, we have got the averaged circuit dynamics and we have added the perturbation. Now we have to separate the perturbation. We have to separate out the perturbations and steady state quantity. So let us look first into the steady state quantity. That is your L derivative of IL. The average value is 0. So L dIL by dt is 0. So that means your 0 is equal to Vn, just the average quantity minus IL into RL plus R1 minus 1 minus D into V0. V0. This is equal to 0. Okay. Similarly, for your inductor current, you have minus V0. 0 is equal to minus V0 plus 1 minus D into IL. Okay. So these are the DC quantities. Right? But we are interested in the AC quantity. That is this equation. This equation we have to simplify this. So whatever the DC terms we will ignore because they are already taken into account. Now we just need to focus on the AC terms, right? So we write L DIL perturbation of dt, that is equal to Vn perturb minus RL plus R1 into IL perturb minus 1 minus D into V0 perturb plus D perturb into capital V0, and you have plus D perturb into V0 perturb. Now with this, what are we supposed to do? We will set this to 0. We ignore this, right? So we get our L DIL perturbation by dt, that is Vn perturb minus RL plus R1 into IL perturb minus 1 minus D V0 perturb plus D perturb into V0. Okay. Next, we have to be concerned about your capacitor 1, right? Capacitor 1 is fairly simple. So we get it into C dV0 perturbed by dt, that is equal to minus V0 perturbed by R plus 1 minus D into IL perturbed minus D perturbed into IL. Okay, these are the equations for the capacitor current dynamics. So we have got these equations. Now, how do we represent? We can represent it in a AC equivalent model, right? What do we have? You have your input perturbation is over here. You have your L, this is your IL perturb, right? Then you have your RL plus R1. This is there. Then you have your minus plus D tilde V0. Then this is your, and this voltage over here, that is your 1 minus D into V0 perturb. Okay. And we consider DC transformer. This is your V0 perturb, right? And you have this is your 1, this is equal to 1 minus D. Right? So this current is actually your 1 minus D into IL perturb. This is your R. This is your C. So this is your IC. This is your V0 perturbed by R, right? And then you will have this current source also here, that is D perturbed into IL. So this is your AC equivalent model. Any queries about this?
Sir, that turns ratio, is it 1 is to 1 minus D or 1 minus D is to 1?
This is your input. Over here we see a 1 minus D into D output perturb. Yes, it should be like this, right? Because we know for a transformer you have V1 upon V2 is equal to N1 upon N2. Right? So what is our V1? Our V1 is so V1 is 1 minus D into V0 perturb from V0 perturb. This is N1 upon N2. Okay, okay. So your N1 upon N2 should be equal to 1 minus D upon 1. Correct, correct. You're correct. Sorry. So this is 1 minus D is to 1. Okay. What about others? Any doubts? Any queries here? Okay, so like what we were trying to do is we have some parasitics. That is, we have a RL and R1, and how they affect our overall AC equivalent model. We will look into that. So now we will have to consider 4 different types of transfer functions, right? We can have 4 different types of transfer functions. So let us consider the simplest one, or one of the simple ones, that is your control to output transfer function. You want to find your, sorry, okay, you want to find your GBD. So GVD is what? Your V output perturbed by D perturbed, right? So in this case, what should we set to 0? What are the perturbations we should set to 0? Actually, I forgot to add one thing. We will have a current source, current load, that is your I output perturbed, okay? That will also be there. So if you want to find your GVD, right? That is your V output perturbed by D perturbed. What and all quantities should be set to 0? What and all perturbation should be set to 0?
V in tilde equal to 0 and I0 tilde equal to 0.
I0 tilde is equal to 0. Okay. So I have a question. Why shouldn't we set IL perturb also to be equal to 0? We just want V output perturbed by D perturbed, right? So all the other perturbations we should set to 0. Why are we not setting IL perturbation to 0?
Since the duty ratio is varying, there will be some variation in inductor current.
Okay. Yeah, that is there. So
we cannot forcefully set it to 0.
yeah, yes. So actually, inductor current is a state, right? Whereas your I output, your V in, those are like your disturbance or your actual system input, right? So that can be fixed. But your inductor current is an internal state. So it is affected by the dynamics of your system, right? So you cannot set your inductor current perturbation to 0. Okay. It is not so, you can't do that. Similarly, you cannot just set your output voltage perturbation to 0. You can't do that because it will be affected by any of the perturbations. Okay. So now, if we set V in perturbation to 0 and I output perturbation to 0, what will change in my circuit?
We can short circuit that input source
Okay.
and open circuit the current source, IO tilde.
Okay, so our equivalent circuit then becomes this shorted. We have your SL. We have this RL plus R1. We can represent it as R equivalent. Okay. Then we have our like that. Sorry. This will be your minus plus D perturb into B output. One minus D is to 1. And then we have D perturb IL. Your capacitor C, that is 1 upon SC, and your R, right? Okay. Then what we must do? So this is your V output perturb, right? And this is your 1 minus D into V output per term. So we can write our SL plus RL plus R1 into this IL per term minus of this minus or plus V output into D per term of S minus 1 minus D into V output per term of S. This is equal to 0. Okay. This for this side KVL we are applying over here. And over here, what we must apply? We must apply KCL. Right? We must apply KCL over here. So how do we apply KCL over here? We have this current IC, I naught. What is this current coming here?
We can use that N1 I1 equal to N2 I2.
Yes. So we have to use N1 I1 is equal to N2 I2. N2 is 1, so I2 is equal to 1 minus D into I1, and your I1 is IL. So you have here, you have 1 minus D into IL per term. Okay. 1 minus D into IL per term minus D per term of IL is equal to V output per term into 1 upon the parallel combination of 1 by SC parallel R. This is your V output per term by S. So, what do we have to eliminate over here? Like, what is the equation we want? We want the equation in terms of V output per term and D per term. But we have it in terms of V output per term, D per term, and IL per term. So what we must do now over here in this case is, we must make our 1 minus D into IL per term, that is equal to your D per term IL plus V output per term of S. What is the parallel combination of 1 by SC parallel R? That is your 1 upon SC into R upon R plus 1 upon SC. Right? So your 1 minus D into IL per term is equal to D per term into IL, V output per term of S into, so this will be RSC plus 1 upon R. Okay. So we have got this. So our IL per term, that is equal to IL upon 1 minus D into D per term plus 1 plus SRC by R into 1 upon 1 minus D into V output per term by S. Okay. So now we have got a IL per term of S. Now we will resubstitute that into this equation. Okay. So we have our minus SL plus RL plus R1 into this IL into 1 minus D into D per term of S plus 1 plus SRC by R into 1 upon 1 minus D into V output per term of S plus V output into D per term of S, V output into D per term of S and minus 1 minus D into V output per term of S. Minus of 1 minus D into V output per term of S is equal to 0. Okay. Now, we have to simplify this. So what we do is we take the terms which are common for duty perturbation in one side. So D per term of S, that is equal to this V output minus of your SL plus RL plus R1 into IL upon 1 minus D. This is one part. And then you have your minus B output per term of S, that is equal to your SL plus RL plus R1 into 1 minus D into 1 plus SRC by R. Okay. Plus 1 minus D. This is equal to 0. Right? So what do we get? We are getting B output tilde of S by D per term of S, that is equal to your B output minus SL plus RL plus R1 into IL upon 1 minus D upon 1 minus D plus SL plus RL plus R1 into 1 minus D into 1 plus SRC by R. Okay. Clear? Any doubts? So now, like these kind of questions you could get in your exam, right? So what you have to write is, they may say, you have to write your B output per term of S by D per term of S. This is your K BC gain into 1 minus S upon your omega 0 into your, let us say, your 1 plus S, or let us say, this will be better like that, 1 plus A1S plus A2S square. You have to write in this format. Then what would you have to do now? See, this is correct. It is not wrong. But you have to get it in this format. So what changes you'll have to do? Silence is golden, but not now. So let us. So yeah, this is a difficult thing. Let me do it. So we have our IL. The average value of IL is actually V output by R into 1 minus D. Okay, so we will substitute that over here. Okay, let us substitute that. And then we will simplify it in this format. Because the question will come like this, right? Then what you will do? So when the parasitics are not there, it is very simple. But when these parasitics are there, they modify it, they make it more difficult. So that you must learn how to tackle it. Right? So our V output of per term of S by D per term of S. Since we are substituting IL is V output by R into 1 minus D, we get V output minus SL, and this RL plus R on I represented by RA into V output by R into 1 minus D square. Here, I will expand this. So how will I expand it is, no, let me first simplify it. So, this R into 1 minus D, I take it over here. So it becomes R into 1 minus D square plus SL plus R E into 1 plus SL R C, 1 plus S R C upon R into 1 minus D. Okay, R into 1 minus D. Now, this R, let us take it in the numerator. So we get V output tilde of S by D tilde of S is equal to V output R 1 minus D square minus SL plus RE into V output into R 1 minus D square by R 1 minus D square plus SL plus RE into 1 plus SRC by R into 1 minus D. So what do we do? This R and R we cancel. 1 minus D and 1 minus D we cancel. So we get V output per term of S by D per term of S. Its V output is common in numerator. So we get R into 1 minus D square minus SL minus RE upon R into 1 minus D cube. No, okay. V output upon 1 minus D into R into 1 minus D square plus SL plus RE into 1 plus SRC. Yeah. So then we have to expand this. So what do we get? We get a V output per term of S by D per term of S is equal to V output into 1 minus D into R into 1 minus D the whole square minus RE minus SL upon your R into 1 minus D square plus S square RLC plus R plus SL plus SRC into RE plus S plus RE. That will be V output per term of S by D per term of S. That is equal to your V output upon 1 minus D into R 1 minus D square minus RE. You take that common. You will get 1 minus SL upon R 1 minus D square minus RE. Right? Okay, over here, you get your R into 1 minus D square plus RE plus S into L plus RC into RE plus S square RLC. Okay. So now, this is your omega Z, right? And this is kind of like your KDC. This is your KDC dash. You have to simplify this, that you have to divide by R1 minus D square plus RE in the denominator, and then you will get your KDC. Similarly, you will get your 1 plus A1S plus A2S square. Okay. So I hope this is clear. Any queries in this part?
Sir, one doubt.
Yes, yes.
Because in all these cases, we are starting from the first dynamical equations.
Yes, yes, yes.
Is there any? Then we developed that equivalent circuit model.
Yes, 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 yes.
So is there any way to directly draw the equivalent circuit by some, like in induction motor, we draw the equivalent circuit and we will assign some physical meaning for R1, X1, like that? Because
This is it because actually, sir, I taught that
because
circuit
these
diagram.
steps are because we have to do so many steps to arrive finally at this. Like in machine modeling, that DQ axis modeling, like in those topics, after deriving the equivalent circuit, some meaning is assigned to terms like speed EMF, transformer EMF, like that. So we can directly draw the motor model even without
Okay.
deriving the. Or
In this case, you could, it became computation. Like this is your equivalent circuit model, like this one. This is your EC equivalent model. So this, once you derive, then you have to change. So there is no actual, like battery and that kind of concept is not over here. There is one issue over here.
okay.
Hmm.
So
You
for a given converter, we have to do all these steps. If such a question comes, then
now,
only we will get the transfer function.
yeah. This can also be done using the matrix method. That you have your A1 matrix, A2 matrix, your on state space matrix, your off state space matrix. Then you average that. That method also can be done. Right?
Okay, sir.
That is a more mathematical method. This is a more circuit based method. So I thought of going through this method so that you can get this circuit model. Because sir has also taught the circuit model this good. So I thought of showing this. Okay, but the other way also you will get the same answer. There is no doubt you will get the same answer. And that is, I think, more mathematical because you don't have to draw this and check it and find the KCL, KVL. That would be more faster in that case. Yeah. Yeah. So
Yes, sir. Yes, okay.
this one I showed for your output voltage by duty, control group transfer function. So this one is used for voltage mode control. But the reason I went through all this, that is through these methods, that I got this and I have got this AC equivalent model. This is for deriving your current mode control thing. Okay, so for that, let me show you how do we consider for current mode control. So when we go for current mode control, what do we assume is this IL per term. This IL per term is approximately equal to your IC per term. And IC per term in this case is your control current or your control input. So okay, so let me draw the block diagram. It will be better if you understand that way. So now I'm talking about current mode control modeling. Right? Modeling in current mode control. So in current mode control, what do we have? We have our current reference IC. Current goes, touches, goes, touches, goes, touches. Right? So this is your IC. And based on the IC, you develop a duty. Right? Based on the IC, you are developing this Q and this is your DT. So in current mode control, we will change this IC. This IC can be made here. This IC can be made over here. Okay. And then your duty also will get changed. So what are we doing in current mode control? We are controlling IC. Okay, this peak reference we are controlling. So you must not get confused that this IC is your capacitor current. You must not think that this is your IC, right? You might get confused that this is also IC, that is also IC. Because in the questions, it is also come like that, right? So that capacitor current, that IC is actually your peak current. That is your peak current. Okay. So when sir has shown your first order, a very simple approximate method for you to derive a transfer function. So that you can derive a transfer function. In that, what do? Is we consider that the average IL, or that is your IL per term of S, that is approximately equal to your control current. So if this has to be true, that means this current triple delta IL is assumed, it is assumed to be negligible. Okay, this is assumed to be negligible. Then only this is true. So this can happen when, in the case that is, you have such a big, this is your T, this is your current, this is 0. So if your current is, say, like this over here, right? This is your current. That means, and this is your the purple one is your IL average, and your orange one is your actual current. Okay, and this, the peaks, which is actually being controlled, right? So this peak is your IC, right? So when this ripple is very small, okay, and that means your this big thing, this is your IL average, right? When your IL average is very much more as compared to your current ripple, when we are assuming that, then we can say your IC perturbation of S is approximately equal to your inductor current perturbation. So this is what we must do when we are doing current mode control modeling. Okay. So what we do then is, we wherever IL perturb of S is there, we substitute that with IC perturb of S. Okay. So what we do there is, we have our, we remember for the boost converter we have derived, we have L DIL perturb of dt, that is VN minus IL perturb into RE, right? Minus plus D perturb V output minus 1 minus D into V output perturb. What we do is, we replace IL perturb by IC perturb. Okay. So we got L DIC perturb by dt, that is equal to VN perturb minus IL perturb RE plus D perturb V output minus 1 minus D V output perturb. What do we do now? We take the Laplace transform. So we get SL into IC perturb of S is equal to VN perturb minus IC perturb of RE plus D perturb V output minus 1 minus D into V output perturb. So we take IC perturb this side. So we get SL plus RE into IC perturb of S, that is equal to VN perturb plus D perturb V output minus 1 minus D into V output perturb. Now, what are we supposed to do is, sorry, you might have come across this question also. You have to get D perturb of S, right? So D perturb of S is what? That will be equal to SL plus RE into IC perturb of S by V output, right? Then minus VN perturb by V output plus 1 minus D V output perturb by V output. So it would be like the question would come, you have your D perturb of S is equal to A, let us sample A. You have your, okay, A11 IC perturb of S plus A12 V in perturb of S plus A13 V output perturb of S. So you have to find these coefficients A11, A12, A13. Okay. And not all questions will be all these big, lengthy ones. Many questions you will find they are just the steps, small steps. Because in the exam, you could not be expected to derive a very large transfer function. There might be one or two questions like that, but there are certain questions which are these small incremental steps. And regarding the exam, I'd like to tell that this is a very difficult subject. Very difficult subject is true, but you try to scan the question paper, you see, you start solving the questions which are easy, which are simple. You first solve those questions and then you go to the difficult questions. Okay. And this is a time, but MCQ based or objective based uh, exam. So what you must do is you must first solve simple questions because you can't waste time. Like that first sum, there's fourth sum which we did, that is a big sum. If you get stuck and spend your time there, cannot do the easy questions. So you first solve the simple questions. And if you are doing any question, you are solving some question. Okay. What I'd suggest is you write what is given. Okay. What you have to find. You write it down and keep. Okay. And you start the question. Okay. You start solving the question. But assume you get stuck. You get stuck at some point. Then you leave it there. You don't spend your time thinking. You leave it over there. And since you have written what is given, you have written what you have to find, you don't need to again go back and read the question. Right? You're saving that time. You already written this is given, boost converter, this is V in, V output is this much. I am to consider current mode control, this is my switching frequency, this LC. I have to find what is my RHP 0. Right? So you don't need to again go back to the question and read it. So that's why you save time. So first you solve the simple questions which you know. And if you solve some question and you get stuck in the question, you have already written what information you need. So you don't need to again go back and read the question. That is the second point. Then many questions will be set in such a way that it is going in a stepwise sequence. So you carefully read the question. Like the first question will be first step. Next question is the next step. Third question is the third step. Like that. Okay. So in that manner, you go. In that manner, you try to understand the question. Because here in this case, D per turb of S is A11 IC per turb of S plus A12 V in per turb of S plus A13 V output per turb of S. Assume this is there. In the next part, you might have some SCV output per turb of S. Let me just show it because let me just do that actually because it is there. So this is for the D per turb of S. We get it from the inductor current dynamics. We will now go for the capacitor current dynamics, capacitor voltage dynamics. So that we know how it was. C dV output per turb by dt, that is equal to your minus V output per turb by R plus 1 minus D into IL per turb minus D per turb into IL, right? So what we do is we take the Laplace transform and IL per turb we replace by IC per turb. So we get SC V output per turb of S is equal to minus V output per turb of S by R plus 1 minus D into IC per turb of S minus D per turb of S into IL, right? So if you'll observe, the question might ask SCB output per turb of S is what? It is what B11 of B output per turb of S plus B12 IC per turb of S plus B13 D per turb of S. So you have it in this form. Now, if you notice carefully, sorry, This also is V output per term of S. This also is V output per term of S. If you want to do further part of the question, you have to take this over here. But for this intermediate step within the question, you don't need to do that. Yeah. You don't need to do that. Okay. So let us continue. So we get SC plus 1 upon R, V output per term of S. That is equal to 1 minus D into IC per term of S minus D per term of S into IL. Right? So now we have to substitute IC per term of S over here. So this is your, no, you don't have to substitute IC per term, you have to substitute D per term of S. Okay? This is your D per term of S. Now, you know for your boost converter, IL is actually V output upon R into 1 minus D. So that also you put over here. So we get your SC plus 1 upon R, V output per term of S is 1 minus D into IC per term of S minus V output by R, 1 minus D. The bracket, what do you put? D per term of S is this SC plus RE. SL plus RE. IC per term of S minus D in per term of S minus 1 minus D into V output per term of S. This whole multiplied by 1 by V output. So V output get cancelled. So you get it in the form of SC plus 1 upon R, V output per term of S. This is equal to 1 minus D IC per term of S minus your SL plus RE IC per term of S by R into 1 minus D. Then you have your plus V in per term of S by R 1 minus D. And you have your plus P output per term of S by R. Okay, you get it in this form. So now, you simplify this further. This will be plus, right? This plus, so this plus, so this will be minus. So V output per term of S, we take it here. So we get SC plus 2 upon R, V output per term of S, that is equal to your 1 minus D minus SL plus R E from R into 1 minus D IC per term of S plus V in per term of S by R into 1 minus D. So we can write it down as V output per term of S into 1 plus S by 2 upon RC into, this is actually your R by 2, sorry, into 2 by R. That is equal to your V in per term of S, R 1 minus D plus this. How do you simplify this? You make this as 1 minus D, you remove common, or you do 1 minus D R into 1 minus D square minus SL plus RE, the whole divided by R 1 minus D into IC per term of S. So we get V output per term of S 1 plus S upon 2 upon RC into 2 by R. This is V in per term of S by R 1 minus D plus IC per term of S into R 1 minus D the whole square minus SL plus R E into R 1 minus D. Okay. If you want to find the control to output transfer function, that is GVC of S, that is V output per term of S by IC per term of S, then we have to set V in per term to be equal to 0. So then what happens? You get V output per term of S into 2 by R into 1 plus S upon 2 by RC, that is equal to IC per term of S into R 1 minus D square minus RB minus SL upon R into 1 minus D square. So you get it as V output per term of S by IC per term of S, that is equal to R by 2 into R into 1 minus D the whole square minus RB into 1 minus this SL by R 1 minus D square minus RE, right? And then, sorry, in the denominator you have your 1 plus S upon 2 by RC into R into 1 minus D the whole square. Okay? So then we can simplify this further. GVC of S is equal to R by 2 into R 1 minus D square minus RE upon R 1 minus D square into 1 minus SL R 1 minus D square minus RE upon 1 plus S by 2 by RC. So this GVC of S is your KDC gain into 1 minus S upon your omega RHP upon your 1 plus S upon omega P. Okay. Where your KDC is your R by 2 into R 1 minus D the whole square minus RE upon R 1 minus D the whole square. Your omega RHP, that is equal to your R 1 minus D square minus RE upon L, and your omega P is 2 by RC. Okay, it is 2 by RC. Any questions regarding this? Because it's a difficult thing. If at any point you're stuck, you can let me know. Okay. So, if you will go back to Sir's lecture and you will see, in Sir's lecture, he has considered your RE to be equal to 0. If RE is equal to 0, that means your KDC is what? Can you tell me if I substitute RE equal to 0, what will be my KDC?
R by 2.
It will be R by 2, which Sir also got. And if your RE equal to 0, what is your omega RHP?
R into 1 minus D square by L.
R into 1 minus D square by L. Okay. So that's why these parasitic resistances, how they affect your DC gain. Okay. In certain cases, you can neglect them. In certain cases, their effect is there. So in the exam or in your assignment, if these questions come, you consider your RE, etc. to be there. And then accordingly, you can, if your RE is supposed to be 0, you change it to 0. Right? Like in the exam, if they don't give you any parasitic values, if they say your parasitics are 0, you don't take RE. But if they are telling you have some parasitics, then you incorporate this RE. Okay. So now, what I'd like to point out is this is actually a first order system. This GVC of S for current mode control is first order. Like what it is doing is your inductor dynamics. It is pushing to a very high frequency. So your inductor acts like a controlled current source. So that is the requirement, or that is the advantage of current mode control. It makes your dynamics first order. And that is very useful. It becomes easier to design a controller for current mode control. But what you must remember is your omega RHP does not change. Okay, your omega RHP does not change. Omega RHP is same for voltage mode control, for current mode control as well. Only your effective characteristic equation or your transfer function gets modified. in this way. Okay. So apart from this, any doubts, Parvati, Arun, HP?
Sir, is it possible to do all these steps in MATLAB as you shown in the previous class?
Uh, these steps in MATLAB is difficult because I have also tried. It is quite difficult actually. Mm, I have actually not been able to get it. So this is
Okay,
difficult.
okay, okay.
I don't know. There may be softwares like Mathematica, all that, but I don't have the license for it. But these ones are a bit difficult actually. Then what you would have to do is you write these equations. You can replace IL tilde by IC tilde. So differentiation has to be converted to SL. That also could be possible. Maybe this tilde sign might be difficult. This it might be possible. You'll have to check this one. Because to what extent I remember trying, I wasn't able to do it. But maybe I should have tried it more harder, but you can do. But rather than spending time there, you could start with the simpler case. Ideal case, you derive the transfer functions for input impedance, output impedance, for GVD, for your GVG, for your GVC in case of current mode control. You get an idea of these transfer functions, like how they actually affect your response, right? Once you get an idea of that, then you can try to, code it or etc. That's the way.
Okay, sir.
Okay. So I'll just give a brief recap. So what we did is we studied small signal modeling. We have various transfer functions you have. These are the important transfer functions. We consider what is a DC-DC converter. We average over the switching time period T. Then this is how these transfer functions affect your output voltage perturbation. What is a transfer function? It has a DC gain. It is second order. It can be underdamped, critically damped, overdamped, depending on value of zeta. This how the response will change. Input impedance will come out as an improper transfer function because the degree of the numerator will be more than the degree of the denominator. So it cannot be physically realized, but input impedance is something we use as a notation. It is not something actually there as a model which we use. Okay. For the DC-DC converter, it is actually a voltage source. We use a DC-DC converter to supply voltage. We regulate the voltage of the DC-DC converter, so its output impedance should be as low as possible. That is set out by S. Input impedance, the degree of numerator is greater than degree of numerator, so it is not physically realizable. Input impedance comes into the picture when we are considering maximum power point tracking. Okay, so for solar panel, etc., as we have talked about. So then the Z input of S has to be adjusted. But usually we are just matching the DC part of the input impedance. Because your boost converter solar panel is very slow as compared to a boost converter. Next, if we are considering EMI filter, in this case, all the high frequency S terms are very important. Because your EMI filter dynamics should be much faster than your DC-DC converter dynamics. That is, we don't want the EMI filter to be slow down your converter. Okay, so that's how EMI filter has to be designed. And why do we need an EMI filter? Because our converter generates harmonics and their noise. So this is your input impedance. Then what we discuss, what are the steps to follow for deriving a transfer function? The differential equation we have to write, we have to average it out, we have to add the perturbation, we have to neglect the higher order perturbations, then we have to find the AC small signal model. So for that, we took a test case of a boost converter. We found the various state space equations. We averaged it out. We added the perturbation. We got a AC equivalent model. And then we tried to find GVD, which is we found to be very difficult. Maybe input impedance or something else might have been easy, but we don't know. Took a lot of steps. We found out V output per turn of S by D per turn of S. This for voltage mode control. You notice this is a second order system. And because usually in a boost converter, LNC we decide in such a way, this designed like that, so that it acts under damp. Okay, so that could sometimes result in oscillatory behavior, which is not desired. Okay, then we have talked about current mode control modeling. How we have this IC reference which we have to adjust. And this is valid when we consider that the average inductor current is much more than your current ripple. And then we did the modeling, we replaced IL per turn by IC per turn. And then we got the duty per turn equation, and that we substituted to get the output per turn. Okay, so we found the GVC of S for current mode control. We found that it is first order. Okay, it is a first order. The RHP0 location does not change. The pole gets changed. The pole becomes a different pole. Okay. So this is for current mode control, the RHP0 and the pole location. Similarly, you could also find your you could practice finding out your input impedance and output impedance, etc. You could see what is the effect. Another point I'd like to bring to your notice is for current mode control, KDC is R by 2. Now your R can change, right? Your load resistance can change. It can become different. So current mode control suffers from poor load regulation. Because the DC gain is dependent on R, the pole location also is dependent on R. Okay. So your R, if your R changes in a wide range, whatever controller you have designed, considering this transfer function, it would not be valid because that's got changed. So in that case, you'll have to redesign your controller or use different set of gains. In the case of voltage mode control, you got it to be V output per turn of S by D per turn of S. It is given like this. It is a second order, but the RHP0 remains the same. So voltage mode control is not that much dependent on your load resistance, but voltage mode control gets affected a lot by your your input voltage. This dependent on input voltage. Because if you see over here, if you see this expression, it is V output upon 1 minus D. But in your boost converter, approximately we can take V output is V in upon 1 minus D, right? Now, so that means it is dependent a lot on the input voltage. If your input voltage magnitude will change, then your voltage mode control, the DC gain itself will change. Okay, your DC gain gets affected, right? So that is one of the reasons that voltage mode control is dependent a lot on the input voltage, but not as much dependent on your load resistance R. But if you see in the case of current mode control, although this transfer function GVC of S, it is approximate and it is first order. It is like a very rudimentary basic transfer function. It is dependent on KDC. And KDC, in the KDC expression, you are not seeing input voltage, right? So current mode control is very much kind of robust as compared to variation in input voltage as compared to voltage mode control. Okay, it can kind of filter out the perturbations of input voltage. Okay. Okay. So any other queries, Parvati and Arun?
No, sir. Thank you.
Okay.
Sir, general,
Mhm.
regarding the final exam, how can I prepare for that? It is a credited course for me, so I'm very much worried about the credit. So if I'm thorough with the assignment questions or practice,
If I to my knowledge, there is a ratio. Assignment questions will come like 50% of your question paper questions will come from the assignments. Will be related to the assignment questions. Then there is some recall type of questions where you have to recall the concept. I think that is 20% or 30%. And there are certain questions which are open-ended. Open-ended questions are like kind of not exactly come from what sir has taught. It is like a little bit advanced taught. Like, in your 10th and 12th, you would have had this higher order thinking questions or something like that. Those kind of questions. Okay. So first is assignments. You have to get it right. Assignment questions, whatever type, modifications, thing, permutations, you try to understand assignment questions very well. Be very thorough with the assignment questions. Then some of these questions which I am doing also over here, you can go through, right? And preferably make notes. Are you making notes of the, what you say, the course?
Yes, sir.
Yeah. Notes are mandatory because you cannot go through the videos all over again. No. And many things in the videos are like, demonstrations, where sir is demonstrating some simulation, right? You will not have time to run all the simulations, but there are some points which sir will repeat a lot of times. Okay. There are certain things which sir will repeat a lot of times. Those you kind of note it down very well.
Okay, sir.
Yeah. And this basic of this circuit averaging, right? This DC circuit averaging, this AC circuit modeling, transfer function, finding the transfer function, omega RHP, like these kind of things, right?
Yes, sir.
These are this will all come, right? These things are the basic
Yes.
things. So in the exam, you will not be told no to what would be the outcome of a simulation, something like that will not be asked to you. You will be asked something mathematical. Either it will be very mathematical, or it will sometimes, in some cases, it will be some theoretical concept. No, like that.
Okay, sir.
Yeah. And
Thank you, sir.
yeah, you can try to find some easier ways to solve questions. And you would have prepared for lots of what you say, these entrance exams, right? So that same strategy you must follow. Like if you're not able to answer a question, you leave it. Don't waste too much time on it. Complete all the simple questions. This doesn't have negative marking, right? So that's an advantage you have over here. And then you go back to your difficult questions which you are not able to solve, right? So the goal and objective is, if you know a question, how to solve it, you first do that, then you go to the next question.
Sir.
Okay, so all the best. Yeah, I think we have done halfway through the course. So the next half also will be there, right? So hang on, hang in there. Yeah. So I'll say. And if you have any suggestions, you can let me know also. Okay. Okay, then I'll stop the meeting. Thank you for joining.
Thank you, sir.